We are now going to look at the force law for simple harmonic motion. Earlier, we had understood that not all periodic motion can be considered simple harmonic motion. For example, if you are going from your home to your school and coming back to your home from your school every day at the same time, it is fulfilling the requirement for being a periodic motion, but it is not an example of simple harmonic motion. In order for an object to be undergoing simple harmonic motion, it has to fulfill a very simple requirement. The displacement of the object has to be a sinusoidal function of time. So this is how we describe it mathematically. So xt is the displacement of the object, and here is the sinusoidal function that relates the displacement with time. Now, based on this definition, we can now derive a force law. So we can understand how the force varies during a simple harmonic motion as the force acts on the object. So how do we do this? We will use some basic definitions that we have already done earlier to get to this point. How? We know that differentiating displacement with respect to time gives us velocity. We also know that differentiating velocity with respect to time gives us acceleration. So I can say that if I were to differentiate displacement twice with respect to time, it will give me acceleration. Now let's use this result in order to derive the acceleration for simple harmonic motion. So here is our displacement relationship. X of t is equal to a cosine omega t plus phi. So in this case, omega is the cyclic frequency, phi is the phase lag or lead, and xt is the displacement with relation to time. So if I differentiate displacement once, I am getting a new relationship here, that is negative a sine, and there will be an omega here, omega t plus phi. So I have differentiated displacement with relation to time once, and this has given me a function for the object's velocity at any given time. If I differentiate this again, so if I differentiate this function twice, so d2x by dt square gives us negative omega square a cosine omega t plus phi. And as we saw earlier, this is the function for acceleration. Now, if you look at these three equations, and if you were to compare equations 3 and equation 1, you would notice that we can express the acceleration in terms of displacement, because this is common to both. A cos omega t plus phi is common to both these equations. So we can rewrite this equation, equation 3, as at, that is acceleration with respect to time, is equal to negative omega square. So this entire term is equal to what? X of t. So this becomes x of t. So we can say that the acceleration of the object at any given time is negative omega square x of t. Now we can use this result to derive the equation for force, or the law of force for simple harmonic motion. Now, by Newton's law, we know that F is equal to m times a. Here we are dealing with a time-varying acceleration or a time-varying force. So I can say that F, function of time, is equal to mass multiplied by a, the function of time. Now, using the earlier result that we have already derived, we know that F of t can be written as negative m omega square x of t. For an oscillating system, the mass is constant, the frequency of oscillation, if it is not changing. Let's say that the system is oscillating at 50 hertz and has been doing this forever, then both the mass of the system and the oscillation of the system are constant. So their multiple will also be a constant, their product will also be a constant. So I can say that f of t is equal to negative k x of t, where k is equal to m omega square, or I can write omega is equal to under root k divided by m. So this relationship here is what we were looking for. This is the force law for simple harmonic motion. What does this equation tell us? Just glancing at it, I can see that there are no square terms of x, there are no cubic terms of x, there is only one term here, and that term also has a power of 1. So that tells me that this is a linear equation, which is actually a blessing for us because linear equations are easier to deal with mathematically. So an oscillator, any kind of a system undergoing SHM, which is following this force law, has a special name. It is called a linear harmonic oscillator. And this is our starting point for analyzing how forces interact with an object during simple harmonic motion. Now, if you go more deeply into the analysis, if you take up engineering as a career or advanced physics as a career, you will find there are many examples. In fact, most examples in nature do not follow this equation. If you were to write a force equation, for example, imagine a aircraft wing which is flapping up and down in turbulence. The equation for that wing would not be this simple. It would contain square terms, it might contain cubic terms, or even higher degree terms. So those will not be linear harmonic oscillators. But for the purposes of this class, we are going to focus our attention on systems which are obeying this law, which are acting as linear harmonic oscillators.
Manorama Horizon, learning made simple.